Hello, everyone, and welcome back. I am so thrilled to have you here for this explainer, which is proudly brought to you by Forge College. Today, we are crossing a massive threshold in our journey through the Ethereum fundamentals track. We're officially stepping away from our theoretical blueprints and getting our hands dirty with some real, actual testnet execution. If you've been following along with our capstone project, you know we've been designing an end-to-end transaction simulation. Well, today is the day we configure the environment to actually run it. So let's get into it. Okay, let's dive into this blueprint for the day. We'll do a quick recap, gather our workshop tools, set up our environment, write the execution script, run some necessary verification checkpoints, and wrap up with our next steps. Let's get building. Starting off with Section 1, Intro and Recap, from Blueprint to Workbench. So, in our previous lesson, we carefully drafted our plans. Now, we need a physical workspace. Just to give you a clear map of exactly where we are, we just finished Step 1, planning the simulation. We're currently right here in Step 2, configuring our testnet environment. And I really can't emphasize this enough. We literally cannot broadcast any of our planned simulations to the network until our tools are perfectly calibrated. It's like trying to launch a rocket with a broken control panel. Now, what's really interesting to consider is the main question we have to answer today. How do we actually turn our theoretical simulation blueprint into a working, breathing Ethereum transaction? You know, it's super easy to talk about transactions in the abstract, but bridging that gap between theory and actual code, that's where the real magic happens. Moving right along to Section 2, Gathering Your Workshop Tools. Let's look at the parts list. Every good engineer inspects the raw materials before firing up the assembly line, right? Here's our required toolkit for today. We need Node.js and NPM to run our scripts and manage our packages. Then, we've got our software wrenches and safety goggles, the ethers library, which gives us all the transaction functions we need, and .env, which keeps our secrets safely hidden away. We're also going to need an RPC endpoint to connect to the testnet, and of course, a private key to sign our script. And that key needs to be held very, very securely. Before we go any further, I want to clarify one absolutely critical concept, the RPC endpoint. I want you to think of an RPC endpoint as a direct phone line straight to the Ethereum network switchboard. It's essentially a URL that acts as your portal. It takes your local scripts requests, translates them, and hands them right over to an actual Ethereum node on the testnet. Without this, your script is basically just talking to itself in an empty room. Which brings us to Section 3, Setting Up the Environment. It's time to prep the workbench. All right, let's lay down the foundation for our code. These are the sequential shell commands that will spin up our Node.js project. You'll just pop open your terminal and run mkdir capstone setup to create the directory. Then cd capstone setup to hop into it. Next, run npm init-y to instantly create your package.json file. And finally, npm install ethers.env to download those crucial software wrenches we talked about a minute ago. Just 4 simple commands and your foundation is officially poured. And now for a very serious, though entirely preventable, warning. You absolutely must create a file named exactly.env to hold your RPC URL and private key. I want you to think of this .env file as a reinforced titanium safe. We hide our private keys in there, and we tell our version control systems to completely ignore it. We do this so we don't accidentally push our keys to a public repository and inadvertently fund some hacker's beach vacation. Seriously, keep it local and keep it safe. All right, Section 4, Writing the Script. Let's assemble build-and-sign.js. This is the absolute core artifact of our explainer today. This is the program that takes our parameters, constructs a valid transaction envelope, and programmatically signs it. And this brilliantly illustrates how we can break the process down into 4 elegant steps. First, we connect our provider and wallet, using the secrets hiding in our .env safe. Second, we build a simple transaction envelope, just sending 0 way to ourselves to test the pipes. Third, we reach out to the network to estimate the gas and fee data, pulling those latest EIP 1559 metrics. And finally, step 4, we sign that transaction with our private key to generate a raw hex string. Now, while you're populating that transaction envelope in step 2, I want to emphasize one specific number, 21,000. For our capstone, this is the standard gas limit we hardcode into our script. We usually wrap it in a hex conversion function because 21,000 is the exact standard amount of gas required for a simple transfer on the Ethereum network. Once you save your script and run node build-and-sign.js in your terminal, here is exactly what you're looking for. The expected output is a console log saying signed raw followed by a beautifully assembled massive hex string that starts with 0x. If you see this popping up on your screen, congratulations! You have a fully signed payload that's locked, loaded, and ready to be broadcast. Moving to Section 5, Verification Checkpoints. Time for some system diagnostics. Look, every good inventor runs a thorough system diagnostic before hitting the big red launch button, right? So pre-flight check number 1, is the wallet configured and accessible? We have to be absolutely sure that our script can actually read the .env file, grab the private key, and derive a public address from it without throwing a nasty error. To test this out, you run a quick one-liner in your terminal. If it succeeds, you'll see a 0x prefixed 20-byte Ethereum address pop up. That tells you the wallet is perfectly wired up. But if it fails, you'll likely get hit with a giant error complaining about environment variables. If that happens, no panic. Just go check that your .env file is named correctly and is sitting in the right folder on your workbench. Next up, Diagnostics 2 and 3. Is the account funded, and does the script output the signed hex? Basically, we need to know that we actually have the fuel, meaning testnet funds, to pay for gas, and we have to verify that our signing mechanism isn't just spitting out garbage data. So the crucial point is knowing what success looks like. Success means querying your balance returns a number greater than 0 and running your script prints out that long hex string we just talked about. Failure, on the other hand, looks like a big fat 0 balance, or your script just crashing when it tries to get the fee data. Keep in mind, a 0 balance or querying the wrong testnet chain ID will completely halt our simulation before it even begins. Finally, Section 6, Conclusion and Next Steps. Let's pack up our artifacts. All right, it's time to clean up the workbench. You've successfully built a local environment that can construct and sign transactions completely offline, which is honestly a massive achievement. Let's quickly summarize our 3 main takeaways. First, always isolate your secrets safely in your .env file. Second, explicitly verify your testnet connectivity and ensure you're on the correct chain ID. And third, and most importantly for our capstone, save the outputted hex string into a file called sign-tx.hex. We are essentially creating an auditable chain of evidence here: your script, your .env file, and your printed hex. We're packing all these into a folder to take to the testing ground. Which leaves us with this final, somewhat provocative thought. What secrets and actual real-world gas metrics will this signed hex reveal when we finally broadcast it to the network in our next lesson? We've got our blueprint, we've got our fully assembled transaction, and next time we hit the launch button. Thank you so much for joining me for this explainer, which was proudly made by Forge College. I highly encourage all of you to visit our website at forge.college to dive even deeper into this subject and discover a ton of other fascinating Web3 topics. See you next time, and happy coding.